So in 2019, I moved to Singapore, and I also spent a year in MIT. SUTD, this university, was formed in collaboration with MIT, and it was a new university. So to give the new faculty experience, we had the opportunity to spend some time in MIT. I'm also the OMEX associate editor. I've been doing that since 2018. And as of this year, I've started working in Birmingham. So I've been back and forth between Asia and Europe, or the West and the East, quite a few times over the last decade or so. Yeah, so a lot of what I'm going to talk to you today is about phase change materials and how they can be applied to photonics. So for those that aren't familiar, I know a lot of people in Exeter are very familiar with phase change materials, but some might not be online. The idea is quite simple. You have a crystalline material, and you can heat it up with a nanosecond heat pulse, and it melts, it disorders, and the optical properties change considerably. And you can quench it into this amorphous structure if you remove the heat fast enough. And this has a low reflectivity, this has a high reflectivity, this is a low conductivity, this is a highly conductive material. And you can switch back and forth between these materials by heating to different temperatures for different amounts of time. And this can be done millions, if not billions of times. So it's highly cyclable. And in the 90s, these materials were used commercially for optical data storage in rewritable DVDs. And then more recently, Intel have been using the same, almost the same material for electrical phase change memory in their Optane product. It's because there's a large change in resistance. This is a logarithmic scale here when this material switches between amorphous and crystalline states. And people are generally happy with these materials, although I think Intel are not, I think they've just announced that they're discontinuing this product. But generally, on Amazon at least, it has very good reviews. So it's kind of useful. So the history of phase change materials shows that it kind of goes backwards and forwards between optics and electronics. So in 1968, Evzhinsky shows an electrical device that changed phase based on a telluride material. And then slightly later, they showed the same materials could be used for rewritable optical storage. And then in Panasonic, or at the time Matsushita, developed optical rewritable discs based on very similar materials. And then it switched to electrical. So it's gone from electrical to optical and then back to electrical again. And now generally it seems that the research is going back to optical and photonic structures again. So there's this kind of oscillation in the application space. Interestingly, not many people have shown kind of electro-optical phase change devices. So the reason this material is interesting is this huge change in refractive index. So this is a real part of refractive index. So this controls the phase of the light. And this is the imaginary component of refractive index, which controls the absorption or the amplitude of the light. You can see that in the infrared, at least, this famous data storage germanium antimony telluride has an enormous change in refractive index. And the refractive index is very large, generally, in both states. And if you go into the infrared above 1.5–2 microns, and the material, the photons have energy below the band gap, so they're not absorbed strongly. So the material is also transparent, but has a large change in optical refractive index, real part of refractive index. So they have the opportunity, at least in the infrared, to control resonances and path lengths and things without changing the phase. I'm not sure why that happened. So in 2011, I moved to Spain, and we did something relatively, in principle, conceptually very simple, but it's actually quite difficult technically. We patterned a small amount of phase change material on a silicon ring resonator, and showed that we could crystallize this material and switch the resonant frequency of this ring resonator by crystallizing this phase change data storage material. So this is, again, this is a material that was originally developed for data storage. And the reason there's a shift in this frequency is this has a higher refractive index, and it redshifts when it crystallizes because of the higher refractive index. So we see this longer path length and a redshift in this resonance. And we can also switch this back. So we can go from the crystal to the amorphous phase and switch this resonance backwards and forwards. Similarly, in Spain, we made these plasmonic waveguides. So these are surface plasmon polariton waveguides. We launched the light into a surface plasmon mode through these gratings, and it's transmitted along this gold waveguide. And we've covered the gold waveguide in places with GST, and this attenuates the transmission of the surface plasmon waveguide. So we're using the absorption property, the extinction coefficient of this material, to change the transmission. So this point here is where we launch the light. There's a reference scattering particle in this, well, line defect at this point here, so we can normalize the transmitted light. And then we measure the intensity at different positions from the launch site. And then we can make these graphs and show that we can attenuate this is just a transmission line experiment, but we can attenuate the surface plasmon polariton transmission. So these were, I mean, the idea of this was to make some kind of plasmonic RAM, some sort of electrical memory that you could read plasmonically. So this is the reason this GST is shaped in this way. You could pass a current through it, heat it up, crystallize it, and measure the surface plasmon polariton waves through it. So that was the whole idea behind this paper. So I was showing these two papers on the transmission of these surface plasmon polaritons and these ring resonators at a conference in Spain in 2012, beginning of 2012. And then this guy from Bristol came over to me and said, "Wow, this material looks fantastic. Can we make some metamaterials from it?" So that's how I became interested and started doing research into phase change metamaterials. So Martin from Bristol was the one that introduced me to this potential application for these phase change materials. And he had a student that or a postdoc that had finished working in Bristol and took a faculty position in Dalian University called TUN. And in 2012, we rolled out a whole bunch of papers just showing the potential of phase change materials, data storage phase change materials, mostly in the infrared, where we were controlling the phase of the light rather than the absorption, based on GST controlling resonances and meta-atoms. So we were mainly trying to operate above 2 microns, where the absorption is minimal and where we're just having this change in refractive index. So these are some of the devices that one of the first devices that we tried to simulate and test whether the phase change material would be useful. And the basic idea here is that we apply an electric field to one of these squares, and this causes the electrons to move, obviously, in this metallic square, and this will create a magnetic field around it. So essentially, we have an inductor around this metallic square. And then when the electrons are at the end of their path, they're going to behave like a capacitor. We'll have an image charge through this dielectric. So we have some strong electric field going through the dielectric at this point. And then the electrons move in the opposite direction because of this electric field, and it turns into an inductor. So this whole system can be modeled as a LC circuit. So the frequency of an LC circuit is 1 over 2 pi root LC. So the wavelength is roughly proportional to 1 over the square root of LC. And the capacitance for when the material is behaving like a capacitor is proportional to these geometric parameters and the permittivity of the material. And when it's behaving like an inductor, it's proportional, the inductance is proportional to length and inversely proportional to thickness. So you can see that if we substitute these into this frequency equation, you can see that the wavelength is proportional to these geometric parameters, but also dependent on the square root of the dielectric function. So the square root of the dielectric function is the refractive index. So if we can control the refractive index of the material, we can control the resonant wavelength or resonant frequency of these meta atoms, essentially. So that was the whole idea behind this structure, where we have some kind of thin layer of tunable material, so that we can control the resonant frequency of these structures. So these are some of the early simulation results. I should mention SUTD, the university I joined in 2012, when we started working on these materials, was a completely new university. In fact, we didn't even have a proper campus. We had a temporary campus in an old school. And then whilst we were waiting for our campus to be built, our campus wasn't built until 2015. So we didn't have any facilities, we didn't have clean rooms, there was nothing, right? So we were relying on simulations at the beginning. So you can see here from these simulations that in the amorphous state, this structure has a resonant frequency at around 2.25 microns. And then when we crystallize the material, the resonant frequency switches to slightly longer wavelength because the fractal index of the material is larger. So potentially you can make some kind of metamaterial filters that are programmable in the infrared using these phase change devices. So as I mentioned, we didn't have a clean room, but the Harold Giessen's group in Germany, in Aachen, did. And they created very similar structures that basically proved this concept worked experimentally. So they created aluminium square arrays with a very thin layer of GST and an aluminium back mirror underneath. And they excited these plasmonic resonances in these aluminium layers and saw very strong tunability of the resonances when they switched the material between the amorphous and crystalline states. So this was an experimental proof that these data storage materials could be used for programming these mid-infrared metamaterials. I should mention that, this is a very important paper, and I don't mean to be so negative about what I'm about to say, but this is an aluminium resonator. Aluminium melts at around 660 degrees C, which happens to be the same temperature that GST melts. So it's actually highly likely that this structure wouldn't survive many cycles, and quite likely, as you'll see in a minute, that the aluminium will diffuse into the GST and create some sort of alloy that is non-switchable. So gold is a better choice, but still gold is not great. Gold has a melting temperature of about 1,000 degrees C. So we in 2012, 2013, we published a whole bunch of papers showing different metamaterial structures that are all based on the same kind of concept, that we could control resonances with this metal phase change metal structure and using the phase change material to change the resonant frequency of these devices. So these were all simulation papers. But as I mentioned, in 2015, we got a campus with a clean room and we could start making things. So in 2016, we made our first paper, which was based on plasmonic structures on top of GST. And we could show different colors and things that we could create with these devices. As I mentioned, we were using mainly gold metals for the plasmonic elements in these metamaterial structures. You don't really need to understand this too much, but this is a X-ray reflectivity measurement. So if you put a very thin layer of metal on a substrate, you can measure the interference of the X-rays as it bounces around off the surface. And you see these very nice interference patterns. And from this, you can work out the thickness of the material. You can also work out the density and how nice the interfaces are. If you see very nice oscillations, it means the interfaces are great. They're pristine interfaces. If you see no oscillations, it means the interface is very rough or interdiffuse. So we did something very simple. We just put different materials on top of GST because we wanted to make these tunable plasmonic resonators to see which ones liked being on top of GST and which ones kind of interdiffused or became very rough. Because this is fundamentally important if you're going to make plasmonic GST-controlled resonators. But for example, aluminium, this is the red curve is the measured curve here. As soon as we deposit it, it's reacting somehow with the GST and creating a horrible interface, and all of these oscillations disappear. Same is true for silver. Tungsten is a lot better. Gold is really, really nice. And also titanium nitride is really nice. It turns out that even with gold, we notice that there's a little bit of a reaction happening at the interface. So if you have very thin layers of GST, gold is not great either. But titanium nitride is probably the preferred material. And it also happens that titanium nitride behaves like a plasmonic material. It has a negative real part to the dielectric function in the visible spectrum. And that's why, for example, titanium nitride tipped screws look like gold. Their optical properties are very similar to gold in the visible spectrum. So I think titanium nitride is a good choice. Also, is this going to work? The melting temperature of titanium nitride is 3000 degrees C, whereas gold is like 1000 degrees C. So it's when you heat these materials up to switch them, it's highly likely that titanium nitride will survive. And if you need it any more convincing, titanium nitride is a common electrode used in phase change memory, electrical phase change memory. So it seems like a wise choice for if you're creating plasmonic metamaterials that are tuned with GST. In this case, we didn't use titanium nitride, we used gold, and that we had to put a diffusion barrier, silicon nitride, between the gold and the GST to stop strange things happening. But our aim here was to create a transparent metamaterial, the plasmonic metamaterial in the infrared. But it didn't work great. So as you can see here, these are the simulations of where the resonances should be, depending on the size of these plasmonic resonators. Silicon's transparent, intrinsic silicon's transparent in the infrared. So this should be quite a transparent material with nice sharp resonances. But when we did the experiment, although we did see some dips, the resonances have a very low Q factor. But transparent metamaterials are actually much nicer if we want to make tunable beam steering devices or some kind of filters that we can put in front of detectors. But it looked like these plasmonic approaches were not really that suitable. So there was a clue of how we might be able to do these kind of transparent beam steering devices in 2006 at EPCOS, which is a phase change conference that is held in Europe. And this was an abstract published by Energy Conservation Devices, which is the company that Stan Ovshinsky, who started the phase change field, started his company. And back in 2006, it basically described a way of making a beam steering device from GST, where they have an array of oscillators. I think there are 8 of them here with a separation of quarter pi, I guess, between each of these oscillators. And these are written into GST with a laser. And they said that when they shined light through this structure, the material, it was able to bend the beam by around 2 degrees. And theoretically, it should be able to bend the beam by 10 degrees. So this beam bending device was described in 2006. However, they said they wanted to do this at telecoms wavelengths, and the reason was that they wanted to make some sort of multiplexer system for telecom optical communication. And they said that their material was not really, GST 225, the common phase change material, was not really suitable. So they made a completely new alloy for this application that was more transparent at 1550. And they, although I didn't attend this conference, but I downloaded the abstract, they didn't describe the experiment. They just described, they didn't show the results from the experiment in the abstract. They just described the experiment. But it seems that these kind of meta surface ideas, again, Stanoshinsky was ahead of everybody, kind of proposing these things 10 years before everyone else started working on them, which I think is kind of neat. Yeah. So then exactly 10 years later, there was this paper by Nikolai Zolodev's group, where they used a film of GST and they laser wrote these kind of Fresnel surfaces into GST, and showed that they could create different types of focusing depending on the structures they created. So they're using actually dielectric effects rather than plasmonic effects to control the phase of the light for each of these rings to create this focusing point. And then Exeter, David's group, I believe, just a few years later, showed that you could create dielectric resonators from silicon. And then by putting a thin layer of GST, phase change material, in the silicon, you can turn on and off certain resonances in the structure. For example, this electric dipole resonance is removed when you crystallize the material. But it doesn't look like I don't know, maybe you can correct me, David, but it doesn't look like there's much of a shift in the resonance. It's mainly using the absorption effect and the increased absorption rather than the change in the refractive index, the real part of the refractive index, to control these resonant effects. So what we would really like to do is control the resonant wavelength and resonant frequency of these resonances, because then we can create phase arrays and do beam steering, just as this paper from 2006 showed. But it seems like the materials that are available, that most people were using, the data storage materials, are not, they're too absorbing at most of the wavelengths that we're interested in the near infrared and visible. So, for example, if you take these data storage materials, and they were designed for a very specific purpose, which was to store data for 10 years and be able to switch very easily with a visible laser light. To switch a material with visible laser light, you need to heat up the material. So it needs to absorb the laser light. So in metamaterial, transmissive metamaterial research, we don't want to absorb, we just want to control the resonant frequencies. So maybe for different applications like holography or beam steering, there are different requirement sets that we should be focusing on and trying to find new materials to meet those requirement sets. So for example, this table shows the importance of different properties for different applications. So in data storage, stability of the material is very important. We don't want to lose our data if we just leave the disk on our table for a few hours. We want the data still to be there later. But that's not so important maybe for displays. Maybe we refresh the display at quite a high rate. So or for beam steering, maybe for LiDAR, we don't need this kind of archival stability. Whereas we might quite like multi-state or analog transitions in refractive index, rather than just on and off transitions, which are more typically required for digital data storage. So I think there are horses for courses, right? Like we need to develop new materials for specific applications. So yeah, so I'm saying here, new PCMs that should be needed for programming visible photonics and near infrared resonances. So I don't know, I guess you guys know Back to the Future too, right? Okay. This was an advertisement in Back to the Future 2. I think it was for like 2015. And by 2015, they were predicting, and they got a lot of things right in their predictions in Back to the Future 2, but they're predicting we'll be watching Jaws 19 and we would see these holographic billboards. That'd be great, I think, if we could do this, right? We're a bit behind, only like 10 years, well, 8 years behind, but I think we can still aim for having these things. But to do this, we need wide bandgap phase change materials. So typically the data storage phase change materials have a bandgap of less than 0.7 EV, but the wide bandgap for visible light, we need more than 1.5 EV in order to be able to create holograms and things that our eyes can see. So that requires a whole new set of phase change materials. So most of the data storage materials are based on tellurium. If we go up the periodic table from tellurium to selenium, the materials become more dielectric, less metallic. So around the same sort of time, I and also a few others like JJ and MIT and also Southampton, I think we're thinking along the same lines. So maybe we should be looking at selenides and sulfides rather than tellurides for visible phase change elements in these meta atoms. This shows the point. So if we look at antimony telluride, which is a phase change material, the band gap is around 0.5 EV. But if we go to sulfur, antimony sulfide, the band gap opens up to 1.5 EV. So we can open up the band gap by going up the periodic table. And that's what we did. We took antimony sulfide and try and see if we could use it to make phase change devices. There are a few other good reasons. I'm just going to sell antimony sulfide now because I think there are a few other contenders like this GSST and antimony telluride. Out of all of the contending wide bandgap phase change materials, antimony sulfide has the widest bandgap. In fact, it's the only phase change material that's transparent and visible. Also, it's cheap, especially if you exploit poor people in Indonesia to carry sulfur down from volcanoes. I think they only get paid £5 a day or something. It's crazy how much these guys get paid. But this is someone in Indonesia climbing up a volcano and taking down huge rocks of sulfur out of the volcano. I'm not saying this is a good thing, by the way. I'm just saying that that's how it's done at the moment. And if you look at antimony sulfide on Sigma Aldrich, you can see here, what am I showing? Okay, I think I'm just showing the price. Yeah, basically it's 106 Singapore dollars, which is about £50 for 100 grams of antimony sulfide. And price per gram, if I compare antimony sulfide, antimony selenide, and antimony telluride, it's about 20 times cheaper than antimony telluride, and 60 times cheaper than antimony sulfide. I should mention that on the day when I looked up these prices, which was just before the MRS conference, it was Black Friday, so they had Sigma Aldrich had a deal. It's not usually that cheap. And also the earth abundance, if I compare these materials, antimony and sulfur, out of all the contending phase change materials, are the most abundant materials on Earth. So it's sustainable in some way. So I like antimony sulfide. Optically, antimony sulfide has a smaller refractive index change than the other contenders, but it's still considerable. It goes from about 3 to nearly 4 in the near infrared. Obviously, GST is a lot larger. It goes from 4 to 6, but the absorption is enormous in GST. And same for GSST, these two materials have the largest absorption. But if you compare, say, 800 nanometers, antimony sulfide and antimony selenide, the antimony sulfide is transparent, whereas antimony selenide isn't that wavelength. So you do have to sacrifice a little bit of the real part, refractive index change. It's smaller than the rest, but I think it's still big enough to do interesting things. Okay, this is another refractive index part of antimony sulfide in the visible. So you can see that I say it's transparent and visible, but it's really only at the far end of the visible, above 600 nanometers, this material becomes transparent. So we did a whole bunch of tricks in Singapore. The first paper we made was very simple. We just made a very thin film reflector with a mirror, essentially, with antimony sulfide on the surface. And we crystallized it, it turned blue. And then we reamorphized it with a laser and it turned back to pink. So this was the first kind of simple demonstration that you can get nice effects in the visible with this. And the reason we see this large change, it's actually, we're exploiting absorption again. We're not exploiting the real part of refractive index change so much. It starts absorbing at around 600 nanometers. So we essentially built a resonator that resonates on either side of this 600 nanometer line, depending on the phase of the material. So we can selectively absorb or not. And that's why we get this huge color contrast. My friend Joel Yang, is really into making art, which you can only see if you've got an expensive microscope. So his group wrote The Girl with a Pearl Earring into antimony sulfide with do you know a nanoscribe? Do you know what nanoscribe is? It's a 2-photon absorption direct write lithography system. So it uses a femtosecond laser, but he just used his nanoscribe to write this picture. Then we crystallized it, and then in the same area, we wrote the Mona Lisa into the material. But this was just to show that it's cyclable, and we also did some simple cyclability tests. We've made electrical heaters with this material on top, and then again, it's pink in the amorphous state. We crystallize it, it turns blue, and we just put this material on top of a nickel chromium heater and pass a current through it and use joule heat to crystallize it. The cool thing about this material as well is that it's very easy to amorphize different seems like different refractive indices into the material. So it's not just on and off. We can have multiple states. And I think I can explain that. I'm not going to do it today, but it seems that the antimony coordination in the material changes with temperature, and we can lock in certain coordinations, and that strongly affects the optical properties. Other groups have started studying this material now, and they showed that it can be cycled more than 7,000 times if you don't fully switch it, if you just go to maybe one of these intermediate states. So I think it's still a useful material. We've put these things on Mach-Zehnder interferometers on-chip photonic structures. This is with TU Eindhoven. And we showed that experimentally that we can control the interference pattern and get kind of a pi phase shift essentially in the transmission. So this is useful, for example, for setting weights in neural networks, optical neural networks. And we've also applied antimony sulfide to metamaterials and metasurfaces. So the first demonstration, which we haven't published yet, but we will probably, hopefully publish it this year, because just kind of still polishing it. But we made antimony sulfide hyperbolic metamaterials. So these are materials that have very large birefringence. So if a material is just a normal dielectric and it has no directionality to the refractive index, and you plot the K value, you see that we have a circle. If we have a birefringent material, this would become elliptical if it was a dielectric. In hyperbolic metamaterials, we combine conductors and dielectrics together to create highly birefringent materials. And there are certain effects that you get where, for example, you can have solutions which are no longer on a sphere or an ellipsoid, but solutions to the wave equation where you can have extremely large K vectors. So large K vectors means that the material, the wavelength is going to be very small, and you're going to be able to sense things more easily, because you're more likely to interact with anything that you put close to the metamer surface. So there are two types of these metamaterials, type 1 and type 2, and they've been used for a range of different applications, from subwavelength imaging, nanoscale waveguides, biosensing. Oh, and the other thing I wanted to mention, another area that I've worked on in the past is antimony telluride, germanium telluride superlusters. These happen to have hyperbolic dispersion in terahertz regime. So I think there's some opportunities there to create hyperbolic terahertz metamaterials of these kind of superlusters. But I'm talking about the visible now, so that's something else. So this is one of the attempts we made to make a hyperbolic metamaterial. Essentially, we use antimony sulfide as a dielectric and silver as a conductor, and we put a diffusion barrier in between. This is a TEM image. So in plane, in this direction, the electric field feels the silver because it's conducting in the plane. Out of plane, the material is an insulator because you have antimony sulfide. So that is, if we go back, that is, I think, this condition. We have a negative permittivity out of plane, but in plane, we have a positive permittivity. So it's a type 2 metamaterial. So in the crystalline phase, when antimony sulfide's in the crystallized phase, if we look at 630 nanometers, just here where this blue line is, we see that the real part is positive and the in plane, and the out of plane is also positive. So it's basically behaving like a birefringent dielectric. So it'll have an elliptical sphere in K-space. However, when we crystallize the material at the same wavelength, the material now has a negative in-plane real part and a positive out-of-plane real part. So now it's a type 2 metamaterial. So we can switch between type 2 and normal, type 2 hyperbolic metamaterial and a normal dispersion relation for a dielectric by crystallizing the antimony telluride layers in this stack. And that's kind of interesting because you can start to do some interesting things. For example, we put quantum dots that fluoresce at 630 nanometers on top of this structure. And just concentrate on the blue and red lines here. So in the crystalline phase, where we have a kind of elliptical dispersion relation, the material is not, the fluorescent lifetime is very long for these quantum dots. But when we crystallize the material, it has a hyperbolic dispersion relation, so we can have very large K vectors and a range of K vectors, which means there are more routes for the fluorescent particle to fluoresce. There are more options, so it can fluoresce more easily and it can decay faster. So we get these much faster decay rates. And this is kind of interesting for single photon sources. In single photon sources, if you have a single quantum dot, you don't know when it's going to fluoresce. It could fluoresce at any point within a certain distribution of time. But if you can kind of charge up the material, put it into an excited state in a normal elliptical material, and then switch it very quickly into a hyperbolic material, the emission should happen just after you switch it. It'll become much more deterministic because the decay is much faster in the amorphous state. So, and you can amorphize this material much faster than you can crystallize it. So this is kind of the idea behind this hyperbolic metamaterial research. Another thing we've done is created these dielectric metasurfaces. So David's group made GST thin layers on silicon dielectric, but we created the whole structure, more or less, from antimony sulfide. So the resonance is actually in the antimony sulfide itself. The resonator is antimony sulfide. We controlled the size and gap for these, and we demonstrated we could create a whole bunch of different resonances, and this is seen as different colors in the reflection spectrum. And that's nicely shown by these color gamuts here. So this is the gap between the resonators, and this is the distance. Yeah, and under certain conditions, if you get the magnetic dipole and the electric dipole completely out of phase in these resonators, you can get perfect kind of, or much stronger reflection. And then when you crystallize the material, this 600 nanometer starts to be absorbed, so you suppress this condition. But again, we're using absorption rather than the refractive index change. I just want to show you a video of antimony sulfide crystallizing, and then you'll realize there's a problem. So this is a film of antimony sulfide, and you can see the crystal area growing from a single point. And this is under an optical microscope. This is probably now about 100 microns across. And then you see another crystal growing from the edge where it's nucleated over here. So you can see how the material crystallizes. This is known as growth-dominated crystallization. Not many nuclei form. Nuclei are very sparse, and then the material will grow from a single point. The problem with antimony sulfide is that these individual resonators are isolated in this case. So if nucleation happens, say here, it cannot grow and crystallize this one because they're isolated. So this makes crystallizing these materials, these structured materials, these isolated structures, very difficult. So we needed to come up with another solution. Another problem with antimony sulfide is when it crystallizes, it's birefringent. So you get some orientations, polarization orientations, which have a very large optical contrast between the amorphous state. But there are other orientations which are not so large. The contrast is much smaller. So these are, I'm telling you, the dirty secrets of antimony sulfide at the moment. So we have to overcome these problems. One way, an engineering, nanostructure engineering solution for this, for the growth problem and nucleation problem, is not to create isolated structures, but to create nanohole arrays, which also show dielectric resonances. Now, if the material nucleates from this point here, the crystal can still grow across this net, across the whole structure, because the material is no longer, everything's connected. And my collaborators and friends in IMRI, A-star, actually had this idea to solve this problem. And they showed and modeled that this could also be used to create dielectric resonances in antimony sulfide. So they actually created, I think this is around 100 microns by 100 microns, nanohole array, which should have be a Huygens metasurface. But they noticed that there are two distinct regions in here, and this is due to that birefringence problem. So this crystal orientation here has a different orientation to here, and the optical properties are slightly different within this 100 micron square. So that's one of the issues that we're trying to solve at the moment. As I said, in 2006, not 2016, 2006, Strand et al. Suggested that we could make beam steering devices by creating arrays of different sized resonators. And that's exactly what we tried to do here. So we created these nanohole arrays where the holes are slightly different sizes and the resonances are separated by quarter pi. And in the amorphous state, if we scan the light, these are all designed to operate around 700 nanometers. If we scan the transmitted light through it, we see beam bending around 15 degrees or so. And then when we crystallize the material, this is suppressed and the light tends to go straight through. And then if we reamorphize it with a laser, we get beam bending again. So we can achieve these sorts of effects with this nanohole array. And what our ultimate aim is not to use different sized resonators, it's to use the same size resonator, but to gradually amorphize different levels of refractive index so that we can achieve different resonances, not by size, not by the geometry, but by the optical state of the material. Okay, so that's pretty much what I wanted to show you. So this is what I think we have to do next. There's a number of new compositions that are emerging in the last few years that might be useful for dielectric phase change resonators. So it's worth looking at those. We're also working on, and I haven't showed it here, but materials which have phase change materials which have a very low thermal conductivity, which are much easier to heat up when they're on, say, conducting substrates, like plasmonic substrates, or on silicon, which is also very thermally conducting. And we need these low thermal conductivities to make very efficient phase transitions. We're also working on new types of antimony sulfide alloyed with other elements that seem to have smaller grains, which will help solve this birefringence problem. We found something that we can put into antimony sulfide that will open up the band gap even more and just push it a little bit more into the visible. And it still has a large refractive index contrast. And we've also been looking at and thinking about millimeter wave waveguides. So that's the other thing. And I've joined a group or joined a department in Birmingham that has some background in terahertz and millimeter waves. So I'm hoping to be able to collaborate with those guys and others on this subject. For me, I'm also, my plan is to try and support other groups doing phase change research, but I also want to do slightly different things in the future. In particular, I'm interested in sensing, and I have a bunch of ideas relating to biosensing and magnetic field sensing using chalcogenides predominantly, which I'm going to start working on in the coming years in Birmingham. But I'll still do phase change 30% of my time. So that's pretty much summarized what I wanted to say. Antimony sulfide has the widest band gap of all the PCMs. It's programmable we've made programmable structures invisible in the infrared. We've had some success of applying antimony sulfide to program displays, on-chip photonic structures, couplers and things, hyperbolic metamaterials, dielectric metasurfaces. And we've also shown that the properties are continuously tunable. And my plan is to continue working on PCMs, but also develop new sensing technologies based on chalcogenides. I think that's it. Lots of people to thank. So I thank all these guys. And if you want to link to me in LinkedIn, that's a QR code. Yeah. Thank you.